Hey guys, so for today we're going to solve Leecode number 236, lowest common ancestor of a binary tree. And this is my first time solving the problem with you guys, and so please be patient with me. So the first thing that we should do is we should read the problem statement and then finally ask any relevant questions that can help us narrow down our solution. So given a binary tree, find the lowest common ancestor LCA of two given nodes in the tree. So according to the definition of the LCA on Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. So given the following binary tree, root equals to something something 2516208, which is shown here, and for this first example, P is 5, Q is 1, and output is 3. So as you can see here, 3 is the lowest common ancestor. It's the lowest parent that has 5 and 1 as its child nodes. Another example is 5 and 4, and for this case 5 is the output, and as the problem statement has stated, a node can be its own ancestor, right? So that's why 5 is returned here. Okay, so let's first ask some relevant questions. So the first question that we should ask is what is a binary tree? So quickly, what that is. Okay, so another thing that I see right away here is that this is a binary tree, which just means that has two child, left and right, and this is not to be confused with binary search tree. Not to be confused with binary search tree, and which is a tree that is such that left is less than current node, and right childs are nodes that are greater than current nodes. So this is not to be confused with that. So this is a plain old binary tree that has left and right subtrees or left and right nodes. Okay. And let's quickly state our definition of LCA. So lowest common ancestor, and what we mean here is that a parent node, a lowest parent node that contains both P and Q. Okay, so another quick questions right away is let's think about edge cases, right? What are some of the edge cases? So one of the things that may come up is if either P or Q or both don't belong to the same tree, right? So what do we do for this, right? Something to think about as we try to come up with a solution. Okay, so let's first think about different approaches. So let's think about how we can approach this problem in a brute force manner, right? So let's think about brute force solution. And also let's think about optimal solution. And we should probably identify a bottleneck. Okay. So let's see. So how can we solve this problem? Um, so as you can see here, our tree node is defined to be P, and our tree nodes seem to be let's see, containing, actually, where's the definition of a tree node? Right here. It contains a value, its left node, and non-node, right? And we are also given root. Let's see. So right away, what we could do here is we can think about let's see, maybe what we could do is we can traverse, we can do a simple traversal and see if both nodes are contained within a subtree. So let's see, so for example, let's see, we are given 3 as a root, P is 5, Q is 1. What we could do is we can first traverse the left subtree to look for 1, right? And clearly 1 doesn't exist, so that returns none. And now we do the same for 5, so 5 exists. And we do the same for 5, for 1 in the right. So now the question becomes, okay, so let's write this down. So search left for P and Q. So let's think about this. So we could do search left for P and Q, search, we also do the same for the right, search right for P and Q, right? If, so let's think about this. So if none exists, we search the right, search right. So now our right node becomes the new root. Okay, so what we can potentially do is we can recursively check left and see if both nodes within, so let's think about all the different cases, right? So so for our first case, so essentially what I'm trying to say here is that we are going to leverage the fact that this is a binary tree. So with this fact, we can divide our problem up, meaning that we'll search left, we'll search right, and if both exist in left, then we have reduced our problem to only the left side. So now recursively search left, this left becomes our new root, this left becomes new root. On the other hand, if both exist in right, recursively search right, this right becomes new root, but if if both exist in left and right, then at that point we have then arrived to our solution, right? Arrived at solution. And you might be wondering why, and the reason for that is the first root node that P and Q exist for left and right is our lowest common ancestor. Why? The reason for that is because, let's say both of them, so let's say, yeah, so the reason for that is because it's not possible for, since P exists, let's say P exists in left and Q exists in right of the root node, it's not possible for Q to exist in the left node, so there's no point for us to keep recursively traverse to the left and or the right subtree anymore. We have already arrived at our lowest common ancestor. So let's think about the runtime for this solution, right? So because we are repeatedly searching left and right, if you look at this, you know, we are repeatedly searching left, so that's in, so let's say this is a balanced tree, so that's we search n, so we search both left and right subtrees, which result in O of n, and we're doing this n number of times. So let's say the worst case becomes n square, right? Because we are doing this repeatedly for n number of times. So we have n nodes and n searches. So now let's think about bottleneck. Is there a way, so can we not do repeated search? Can we somehow cache our solution such that we don't have to repeat our search anymore? Let's see. So let's think about this. So let's say P is 5 and Q is 1. In our first example, the first thing that we do is we search 5 within our left subtree, right? And it seems that 5 exists here. And we do the same for Q of equals to 1. We search Q equals to 1 here. So 1 doesn't exist in our left subtree. So now when we search in our right subtree, we notice that 1 exists here. So now we have arrived at our solution, right? So let's do another example. So let's say P is 7, Q is 4. The first thing that we do is we search both 7 and 4. So we're starting from root, we're searching for 7 here. We don't see a 7, search a 4, we don't see a 4 here. So we then have reduced our problem to left subtree. So we search left for 7. We go here, we see 5, we see 2, and here we found 7, we see 4. So now we only have to search this subtree. So now we have reduced one level. So now 5 is our new root. We are now doing the same search. We're searching left here. We don't see 7. Doing left here again, we don't see 4. So now we are here. We do search here, right? So we are repeatedly searching 7 and 4. Is there a way for us to not duplicate this work, right? Let's see. So let's think about it. 7 here and 4 here. Let's see, what's the best way to not repeat this work? Okay, so I cannot think of the optimal solution at the moment, so let's try to implement the brute force solution, and then as we code, we'll think of a more optimal solution, right? So this brute force solution may not even pass our runtime test, but we will see. Let's do that for now, right? So So let's define a simple search root and then p. Okay, so let's call this target. So let's pass for now. Okay, so so what we'll do here is we'll search left for both nodes. So what is search going to return? It's going to return true. Let's see, true if exist, false if not, right? So we'll search left, if self dot search, maybe something like this, root dot p q. Let's see, left and self dot search root dot right. So if both of them exist within the left subtree, then we have reduced our problem to the left subtree. So now we are recursively calling lowest common ancestor function on our left subtree. So now our left subtree, our left node becomes the new root, and we'll do the same thing recursively. So we do here, we do here. If for whatever reason actually the first thing that we should do is we should do self search root dot left. Okay, so let's think about this. Okay, you know what? Let's do this again. Let's clarify all of our cases. So p left. Okay, so we'll do something like this: search root p right. We do the same for Q. So we'll call search 4 times for each node. Both of them will search both of them in the left subtree and the right subtree. So this is what we're doing. Do Q here, Q right. Okay. Root. Okay, left here, right here. Okay. P Q. Okay. So now this is where we do our test for different cases. So the first thing that we do is if P left and Q right, or alternatively if P right and Q left. So this is where we have found our solution. So we'll simply return root here, right? So what we're saying here is that if P exists within the left subtree and Q exists within the right subtree, or if P exists within our right subtree and Q exists within our left subtree, we'll return the solution, which is our lowest common ancestor. Else if right, P left and Q left, then we'll call this lowest common ancestor method recursively on the left subtree. Now our root become for the next recursion, our root become the left subtree, the left node is now becomes our root on the next recursion call, and we do the same thing here. Else we'll do this. Okay, so now let us implement our search function. So for this function, or method to be precise, what we are doing here is actually, let me try this again. If p right and q right. We also have to take into account any other special cases. For that, we'll simply return none. If for whatever reason both of them return false from our search, we just return none, right? That would be our special case. So let's us implement our search. So for our search, we can simply do what we could do is we can, let's see, can we do this efficiently? We could do, this is a binary tree, so we are not given, so we cannot do this any quicker. So what we could do here is we can do a simple in order search, right? So first thing that we do is, let's see, first thing that we should do is check if, okay, so we should do that here. So we'll assume that whenever we pass something in search, root is not none, right? So if root is not none, if root equals to none, then we'll return none here. So we'll do that much earlier here. Okay, so now what we have to do here is, let's see, what are we doing? Yep, so that's very important to do. Right, so the first thing we should do here is check to see whether this current root is none, right? If it is none, then let's see, then we'll return false. Else, if root dot value equals to target, so we are also assuming that p and q's are not none, right? Let's see, so let's do that here. Let's do a check here, and p is not none and q is not none, right? Because why? Because if any one of them is none, what would be our lowest common ancestor for all of them? We have so many, it could be any node, right? If any one of them is none, because all of the leaf nodes here contains non-left and non-right. So we'll assume that p and q are not none. So let's assume that. Okay, right. So now if it is, then we return true. Else, so we'll do a simple search and we'll search for our node. Okay, so let's see, so we'll return self.search on our left subtree, so left target, or self.search root.right target. Okay, So what we're doing here is we're traversing through the left subtree and the right subtree. If this equals to valid, if this root value equals to target value, then we have arrived at a node. If not, then we'll keep traversing the left subtree, so root.left, passing in target or right subtree. So we'll go to both left and right subtree and we return the results. And we're doing OR because we only care whether this node exists within this tree or not. So if either one of them is true, then it's true. Okay, so let's quickly run this code to see if it works. And it seems to finish, and with the right solution. So now let's think about how we can optimize this solution, right? We're doing repeated search, so we are wasting clock cycles here by doing that. Can we not do repeated search? Can we do this in O of n time? Let's think about it. Let's see. Let's think about this. So our bottleneck here is clearly our search, right? Bottleneck. So let's think about our bottleneck, right? Search which takes O of n. Can we make our search a little faster so that we don't have to do any repeated search? Okay, so I can't really think of anything else at the moment. I would say this is the most optimal solution I can think of at the moment. Let us try to submit it to see if the runtime is even acceptable. Let's see. Doesn't seem like it. It's taking a long time to evaluate. And we are also getting wrong answer. So let's look at details here. So we passed 17 test cases. Okay, so the problem, so let's see what's going on here. So we have, so let's copy this over. And let's paste it here. Let's copy all of it. Okay, so what's going on here? So let's copy this and put it here. And let's just run this. Okay, so why is this not right? Okay, let's think about it. So we have 3, 5, 1, 6, 2, 0, 8. No, 7, 4. So we are returning null. Why? Okay. So let's think about this problem. Let's think about this special case. Maybe we'll be able to identify where the problem is within our code. So let's copy that and see what's going on here. Okay, so we have 3, we have 5, we have 1, we have 6, we have 2, we have 0, we have 8, then we have null here, and then 7, 4. Okay, so let's space this out. So we have something like this. Right? So this does take a while to space everything out correctly. So let's look at this. So why did our solution not work correctly? So let's go to this again. We have 3 here, we have 5, we have 1, we have 6, We have 2, we have 0, we have 8, no, no here, and then 7, 4. Okay, so let's see. So first thing that we did, so what are we searching for? For this problem, we are searching for lowest LCA for 5 and 4, right? So 5 and 4. So let's see, the way that our code works is we first search for 5 in the left subtree. See 5 here, so 5 exists here. So we also search for 4, so 4 exists within our left subtree, right? So if this works correctly, then we'll get true for this and true for this. So then we would do this PQ So let's see, anything wrong here? So I don't see anything wrong. Okay, so let's step to our code again. So let's say we are searching for 5, right? So starting with root, searching for 5, and our root is 3. We are calling search root. We are searching in the left. Okay, another very important thing that we did not do is we did not check if our current root equals we did not check to see if root equals to either one of the values. Okay, so we should have done that here. Okay, so what we need to do is check if root.value equals to val. If it is, then now the question becomes, what do we set? Right? Okay. So let's do that here. Right. So if root.val equals to p.val, then what we could do here is we could do p left equals to true if root.val equals to p q.val. Then what we could do here is set q. Okay, this is a tricky one, so let's think about this. So we need another value here, right? It checks whether root.val equals to so what we're doing here is that if it equals to p.val, then else false, right? So now we are checking for equality between root and p, and we do the same for q. q cur equals to self equals to true if root dot val equals to q dot val else false, right? So now we have three different booleans that we have to take into account of. So this becomes a little more complicated. So now to make this complete, we have to do is if p left and q cur or p right and q cur okay, so now we are also checking to see if p left and q current, meaning if current node is the same, if q has the same value as root, and we are also checking to see if p right and q cur, meaning if q has the same value as current nodes. So if any one of these conditions are true, then we have arrived at our solution. So let's see if this fixes our problem earlier. Not quite. Let's see. So we have 5 1 5 4. What are we missing here? So let's think about it. So we have root dot val, p dot val, q dot val. Okay. Let's see. So let's see if this works. We do. Let's see. Okay, so let's go through this example again. So this is where our code fails. So let's think about this. So we are searching for 5, right? So we go to left. So let's say that's p and this is q, right? We go left, 5, so left is true, so left return true. So when we call this on p, we'll get true, and then we'll do left, and when you search p on the right as well, we'll get false, right? Because 5 doesn't exist on the right subtree. And we are doing the same for q. Searching left, q is true, left q is true, right? So this, both of this will be true. P left and q left. Okay, so now because that's true, we'll search the left subtree. Okay, so now we are here. So now p cur is true because our new root, which is 5, equals the value of q, of p here. So this becomes true. So our p cur is true, and our q right is true. Okay, so p cur so we have many more cases that we didn't think of here. So let's see, p left is true, q cur is true. Okay, so let's take into account our cur check. So if p cur and q left, right? So if our p cur is true and q left or q right is true, then this is a valid, then we have arrived at our solution. And now we'll do the same for q cur, and we'll do the same for p if p left and or p right. Okay, so this becomes like so, right? So now what we're doing here is that if p current is true and either q exists within the right subtree or the or the left subtree, then we have arrived at our solution. We also do the same for q cur if the current node if the current root matches our q node and p exists within the right or the left subtree, then we have arrived at our solution. So let's see if this works. So this should address our problem prior. Okay, so now let's see if this code works at all. Let's submit the solution here. So let's see if this works. So like I had previously suspected, our solution is not fast enough because the runtime of this is O of n square, right? So now let's think about how we can optimize the solution here. So let's think through it. So now at least our solution will work on all of the cases. How can we make it faster, right? Let's see. So let's think about the fact that this is a binary tree. Let's see. Is there a way for us to save our previous work? For example, as we search for, so let's look at this example. So let's say we search for 5, right? We found 5 here, right? Is there a way for us to cache our search so that our search doesn't take O of n? Cache search. Okay, so maybe we could do, as we call search, we'll keep track of a lookup table where what we'll do is we'll cache our results here. Okay, so let's explore that solution here. So let's see. So what we could do here is we can initialize our lookup here and lookup And what we'll do here is we'll speed up our search by doing something like this, right? So what we'll do is if root.val in, so if it does exist, we'll return the solution here. Let's see, how does this work? So what we can store here is we can store tuples. If we have previously looked up our root and target val, here we'll simply return that, right? Else we do our lookup. We'll keep track of results. Let's initialize it to false, and what we'll do here is we'll do something like this. So let's do something like this, right? Do something like this and something like this as well here, and then what we'll do is we'll update our lookup table here and set it to the result. Actually, you know what, let's pass in our lookup here because we don't know how many times the object will be created. Let's see, can we do that? No, let's not do that. So let's do that here. Let's assume that the object will be created every time. Okay, so let's see, res, right? So let's see if this solution works. So this should speed up our lookup, and let's see if this solution works. Let's see. Okay, so we still run into the same problem of time limit exceed, and yep, still doesn't solve our problem here. Let's see. Oh, here we still have to do this. Remember, we are doing this in tuple, so we'll do here. Let's submit this code again. Okay, we're getting wrong answer. Let's see. Oh, right, we're not returning all over the place today, huh? Let's see, let's run this. Okay, so that works. So let's see. Let's see if this code works. So first we check if root is none, and also we check to see if we have explored this path already, and we'll do tuple of root.val, target.val. If it's within our lookup, then we return the boolean results that we had previously cached. Else, if this solution doesn't exist, we'll initialize some variable res to false, and we'll do, actually it's not quite right, we'll do something like that. Let's clean this code up a bit here. So let's do res equals to false. We'll return res here if root is none. Else we'll search, return res at the end here. So res variable will be will use to store our solution. So actually we can do even better here. If root is not null or none, then we'll do the search. If it is none, then we return res, which is initialized to false. The first thing that we do within this block is check to see if our solution exists within the lookup table. So we do root.val, target.val, which is a tuple, and if it does exist, then we'll do lookup with this tuple as the key. We'll set our res here. Else, if the solution doesn't exist within our lookup table, then the first thing that we do is to check to see if the current root equals to target set res. Else, we do search on the right and the left subtree, store our lookup values here, and that should be it. So let's submit this. Nice. So okay, so we were able to get the solution to work. So we have optimized our search to potentially of constant. So now our search should ideally be of n, because we are caching our search results. So that should be it for our solution. Thank you everyone for watching. See you next time.